So in the last lecture, what we did was we showed how the fundamental equation of the one model can be derived in a framework which explicitly incorporates market. So in a perfectly competitive setup, we could reproduce the basic solution. So now moving on with this one model, one very important concept, okay, the whole idea hinges around this concept of sort of long run equilibrium. And one concept that is crucial to long run is that of steady state. So today we are going to go through the concept of steady state. Okay, so all right, so basically, what we now need is we have looked into the basic setup, right? So now we have the necessary, so to say, to analyze the behavior of the model over time, right? So how the economy is over time. So first we consider the long run of steady state, and then we describe the short run or transition time. Okay, so once we have a look at the long run, after that we will try to analyze, try to understand the short run time, short run time. So, what determines the long run steady? That's what we are going to focus on, right? So, we define a steady state as a situation in which the various quantities, so the various quantities as in the quantity of variables that we have already looked into, these variables, the quantities of them grow at a constant rate, right? So, what is steady state? Steady state is a situation in which the various quantities grow at a constant. Okay. Now, when we say constant, it can be zero also. Now, some economists use the expression balanced growth path to describe the state in which all variables grow at a constant rate, and use steady state to describe the particular case when the growth rate is zero. Okay, so usually when in the long run the various variables are growing at a constant rate, we are referring to that as balanced. For the time being, let us assume that steady state is a situation where the variables are growing at a zero rate. Okay, so in the long run, although variables under their level, they do not actually. Okay, so in the Solus one model, the steady state basically corresponds to k dot equal to zero, the rate of growth of capital over time. Capital as in per unit capital or capital per unit of labor, small k. That the growth rate of that is equal to zero once the economy has the long run. Okay, so if this is the case, then we have already looked into equation 19, and if you can plug in k dot equal to 0 in equation 19, you can solve for k, and you can what you can do is in the equation, whatever value of k you find, you know that by k star, and you can solve for k star. This is once again basic solution equation. Basic solution plug in k dot and it is SFK star is equal to n plus delta, and from that you can easily solve for k star, right? So k star is the is basically it's the value of capital per unit of labor for which the economy has reached a steady. Okay, so k star is the steady state value. So whatever whenever we are going to note a steady state of a certain variable, we are going to use the superscript star. Okay, so in the Solow model, the steady state corresponds to k dot equal to 0 in this particular equation. So this, once you put k dot equal to 0, if you consider the figure, this is the figure that we put. This equation you represent it diagram, then once k dot is equal to 0, then that corresponds to an intersection of the SFK curve with the n plus delta line, because see, this is the point that is right. Because in the equation, equation 19, what happens is SFK is exactly equal to n plus delta times k, plugging in k dot equal to 0. Right? So when once these two entities are equal, that is once SFT is exactly equal to n plus delta times k, that basically corresponds to the intersection. This schedule is scheduled to n plus delta. Right? So the corresponding value of k is denoted by k star in the diagram. This is the value of capital per unit of labor. Steady state is denoted by k star. So what we do is we focus here on the intersection at k greater than, right? And there are two intersections, one here and one here. So we focus on the intersection here, not at the intersection where k equals. So focus on the intersection where k is greater than. So algebraically, k star satisfies the condition SFK star is equal to n plus delta k star. Going back to the equation, SFK star should be equal to n plus delta k star. So since k is constant in the steady state, y and c are also constant, right? So y basically is a function of k and k only. And once you have determined y, you can very easily determine k. I beg your pardon, you can very easily determine c, consumption. Because according to the Solow model, consumption is nothing but a fixed fraction of output, right? So since k is constant in steady state, y and c are also constant at values y star equal to f of k star. So once k star is determined, so y star is also, right? Y star is equal to f of k star. What is c star? C star is a certain fraction of it, 1 minus s times f k star, right? So this is how you determine once solve for k star from here. Next step, you can determine the value of steady state output, which is y star. Y star is a function of k star. So this gets determined, y star gets determined, and c is a constant proportion of y star. So c also gets determined. It's star. So c star also gets determined, right? Steady state values of output and consumption determined. Now, see one thing. So, the neoclassical model, right? So, in the neoclassical model, the per capita quantities of capital, income, and consumption, K, small k, y, and small c, they do not grow in the steady state. This is one feature of the Solow model. So, in the Solow model, small k, small y, and small c are not growing in the steady state. Rather, what's happening is they are getting in level. Their growth is not changing over. Their values are not changing over time, meaning that the growth, if you look into the growth rates of these per capita variables, the growth rate will be equal to k. Okay. So the constancy of the per capita magnitude basically mean that the level of the variables capital K, capital Y, and capital C grow in the steady state at the rate of population, which is n. Because what is K? Small k? Small k is actually equal to capital K by L, labor, right? So it must be the case for K, small k, to be constant in the steady state. It must be the case that capital K and capital L are growing at the same rate, right? Because capital small k is equal to capital K by N. So both the numerator and the denominator has to grow at the same rate in order to ensure that the small k is remaining fixed, constant. So rate of growth of L is N, which is the population growth. We know population growth is constant, and hence capital K or aggregate capital should also grow at the same rate of growth of population, right? So that's the thing. So one should be aware of the fact that the levels of the variables capital K, capital Y, and capital C grow in the steady state at the rate of growth of population, which is n, small n, according to the concept. So the thing is, once and for all, changes in the level of technology will be represented by shifts of the production function, f of KLA. So shifts in production function, shifts in saving rate, and in the rate of population growth, then you can have changes in depreciation rate. So all these have effects on per capita levels of the various quantities, right? So in let's refer to the figure. In the figure, what happens? Um, a proportional upward shift of the production is, consider a proportional upward shift in the production. So there's, let's say, FK shift upwards, and let's say there's an increase in S. So if S increases, then S times Fk, this particular schedule, particular curve also shifts up. And thus, whenever these things happen, whenever there's an increase in the schedule or an increase in S, or it may be a combination of both, the end result is that K star should increase, right? So there's an increase in steady state per capita capital, right? Similarly, you can consider an increase in N, you can consider an increase in delta. There's an increase in N of delta, or it can be a combination of both. Then, if N plus delta times K increase, then this line would move upward, and this is line move, and this is point of intersection, right? So we come down here, meaning that there would be definitely a decrease in the value of K star, right? So you can play around with the parameters, and you can determine how steady state values get changed, steady state values of capital output of something gets changed. So it is important to note that a one-time change in the level of technology, saving rate of population growth, and the depreciation rate do not affect the steady-state growth rates of per capita output, capital, and consumption, which are still equal to zero, right? So, because of this reason, the model, as presently specified, will not provide explanations of the determinants of long run per capita, right? So, in the model as it stands right now, you cannot find any rationale behind long run per capita growth. So for long run per capita happen, you should um, you should experience some exogenous factor, change in some exogenous variable. So how that might happen, we will explain that. But for the time being, in the basic setup of the solar model, it is not possible to experience long run per capita. And increase in long run per capita variables definitely can be uh, uh, their levels. So, and increase in the magnitudes in level of the long run per capita value that can be achieved, but definitely long run growth of per capita variables cannot be achieved solo model. Okay. So for long run growth to happen, you need to have change in some exogenous factor. It can be a change in technology, because technology here is determined by an exogenously given parameter. So maybe if you experience a shift in that parameter, you know that can lead to long run per capita. And how that might happen, we would come to that later on. But for the time being, let us try to explore the implications of the steady state as it stands right now. Okay, so one important implication of the steady state that follows from the basic Solar Swan model is something that is called the golden rule of capital accumulation. And how that happens, what actually happens when the economy has a steady state. How an efficient agent would try to maximize consumption, that could be captured by idea of golden. So, basically, let us consider a level of A as in total factor productivity, which is fixed. Okay? So A is given, the values of N and delta are also given. Okay, and for these given parameters, you would find a unique steady state value of K star being greater than 0, right? So for a given level of parameters A, N, and delta, there is a unique steady state value of K star being positive, for each value of saving rate, right? For each saving rate, you get a unique steady state value of capital. Capital as in capital per labor. Now, you denote this relation by K star S. Okay, denote this relation by K star S. Uh, Steady state value of capital. Why S? Because S is to signify the value of the steady state capital for saving rate S. Okay. All right. So if that is the case, then denoting this by K star S, and also with D K star S DS greater than 0. What does that mean? It basically means that as you keep on increasing your savings, your capital stock per unit of labor at the steady state, that keeps on increasing. Okay, hence dk star s ds is strictly positive. Now, the steady state level of per capita consumption is, we all know, it's a fixed fraction of output. So what is output? Once capital gets determined at the steady state K star, this is your for given saving rate S, this is the value of steady state capital. So F of K star S is absolute value of steady state output corresponding to saving rate S, and hence C star is the steady state level of per capita consumption, right? C star equal to 1 minus S times F of K star. Okay. Okay, so now we have got the steady state value of per capita consumption, and we know from equation 24, if we use the steady state from 4, let's see what happens. Equation 24 gives us a steady state that SFK should be equal to n plus delta times K star. If SFK star should be delta K star, that is when all per capita variables have stopped growing. The rate of capital per unit of labor is 0. This is what we obtain, right? Now, once we plug in this condition in place of SFK, we can substitute n plus delta times K star, and this is what we get. Simplify this a little bit. This is what you get, C star S. In place of S, just substitute it from our steady state relationship in equation 24, and this would be your expression for C star S, right? Okay. Now, look at the figure, right? One figure. In this particular figure, what we have done is we have taken steady state value of per capita consumption on the y-axis and the saving rate on the x-axis. Okay, so how does per capita steady state consumption change as saving increases? As you can see from here, it first increases, then decreases, right? And maximum value is reached at a certain value of saving. We call it S. So this is the thing. This particular figure basically shows the relation between C star, that is per capita steady state consumption, and S, that is saving rate. And it is, we know this, the relationship between C star and S is replicated in this particular equation, equation 25. So what we are doing is we are plotting this equation, if you like. So the relationship between savings and steady state per unit consumption, right? So the quantity C star, as you can see here, is increasing in S for low levels of S, comparatively low levels of S, and decreasing in S for high values of S, right? The quantity C star attains its maximum here, which is the maximum, when the derivative vanishes. That is when f prime k star minus n plus delta times dk star ds is equal to. So going back to the equation, this is your C star S, partially differentiated with respect to S, and put it equal to 0. This is where there's a change in curvature, or when the maximum is reached. So to say this first order condition, so just put it equal to 0. The first derivative should be equal to 0 for this function maximum, and you figure out the corresponding value of k star. So see here in this particular equation, dk star ds is always positive, right? So it must be the case that the term in brackets should be equal to 0. So the term in square brackets, this should be equal to 0, right? So if we denote the value of K star that corresponds to the maximum of C star by, let's say, K gold, K subscript gold, then the condition that sort of determines K gold is given by F prime K gold equal to N plus delta, because it's very simple from this equation. For the function, consumption function, its maximum term within brackets should be equal to 0. So F prime K star should be equal to N plus delta. And this K star corresponds to the golden level of per capita capital, right? So in place of K star, you can write K gold. Okay. So the corresponding saving rate, we can denote it as S gold, and the associated level of steady state per capita consumption is given by C gold, and C gold is basically something that can be easily determined. It's the consumption is the difference between these two curves. It's the difference between this curve and this K and SFK. So this is the area between these two curves, so to say. So the expression of it would be f of K gold minus plus delta K gold, right? So that would be the expression for consumption, steady state consumption, where the steady state consumption has reached a maximum. We are referring to that as the golden rule value of per capita consumption. So that is the difference between output determined by K gold level of capital minus N plus delta times K gold level of capital. Okay, so this is how we have determined K gold. Yes, this is basically, in a nutshell, this is the idea of golden rule level of capital. Now, what are the implications of it? So the thing is, see the condition, this particular condition is the golden rule condition. F prime gold is equal to N plus 1. Now, F prime K gold equals N plus delta. Here, this particular condition called the golden rule of capital accumulation, and the idea is that in economic terms, or in other words, the economic implication of this is that golden rule result is something which says that if we provide the same amount of consumption to members of each current and future generation, that is, if we do not provide less to future generations than to ourselves, then the maximum amount of per capita consumption is equal, right? So here comes a $1 million question, that how much should be our optimal saving? Like if we save too much, then definitely our current consumption is going to take a back seat. So we would not want that. On the other hand, if we save too little, then definitely that's not going to be good for the future. Future generations don't have much to consume. So that is also not desirable. So in order to understand which saving rate should be ideal, obviously it's the saving rate which leads to the golden level of capital. How that saving rate can be achieved, let's try to understand. So this particular, this particular diagram, if you have a look at it, see this diagram. So what it does is it basically illustrates the workings of the golden, right? So this particular figure considers three possible savings. S1, S2, and S. Right? S gold is something that we are already familiar with. S1 is a saving rate that is little less than the golden rule, and S2 is a saving rate that is little more than the golden rule. Okay, so S1 less than S gold less than S2. Okay, consumption per person, small c, in each case, what does it represent? It's equal to the vertical distance between the production function is Fk, the production function represented by Fk, and the appropriate SFK schedule. So the difference between the Fk schedule and the appropriate SFK schedule captures the consumption per capita, right? Or the consumption per person. Okay, so for each S, the steady state value K star corresponds to the intersection between the SFK curve and the N plus delta K line, right? So this particular intersection of the N plus delta times K line and the SFK schedule, for each of these savings rates, what would happen is the intersection between the N plus delta K schedule and the SFK schedule corresponding to a particular savings rate, this intersection represents the steady state value of capital K star. So for each S, the steady state value of capital K star corresponds to the intersection between the SFK curve and the N plus delta K line. Now the steady state per capita consumption C star is maximized, we know, just now we have seen, when K star is equal to K gold. So there's a K star, and then there's a K star corresponding to which the per capita consumption is maximum, and that K star we are referring to as K gold, right? So this is your value of K gold. K gold is the value for which consumption per capita gets maximum. Okay, so see, for K gold, this is the basically your intersection between the N plus delta K schedule and the SFK schedule, right? So this point, and to draw a vertical line from here to the to somewhere that hits the production function, then this vertical distance, this is the value of consumption, and value of consumption is maximized for this much per capita capital. This is the value of per capita capital for which per capita consumption at steady state gets maximized. That's the golden rule per capita capital. Okay. Now, what happens here is that the tangent to the production function at this particular point, that is corresponding to K gold, is parallel to the N plus delta K line, right? This is the N plus delta K line, and this is the tangent, the FK sheet. And these lines are parallel when we are looking at the maximum value of steady state per capita consumption. So this vertical distance represents the maximum value of steady state per capita consumption. We can refer to that as small c gold. So this vertical distance is small c gold. or the golden rule value of per capita consumption. Okay. Now, since S1 is less than S gold is less than S2, we also see in this particular figure that K1 star is less than K gold is less than K2 star. Right? So K1 star is definitely less than K gold and K gold is less than K2. Now, an important question that comes to one's mind is whether some saving rates are better than some others. Or in other words, uh, are we able to select the best saving rate? So the thing is, we will be unable to select the best saving rate or, indeed to determine whether a constant saving is desirable until we specify a detailed objective function. As you know, we do in some of the future lectures, we are going to specify a particular, a very specific objective function. But we can, for the time being, we can, however, argue, in the present context, that a saving rate that exceeds S gold forever, this saving is gold. Any saving rate that exceeds S gold forever is inefficient because higher quantities of per capita consumption could be obtained at all points in time just by reducing the saving. Now, what you can do is you can consider an economy such that the savings rate is S2. So, an economy that is described by S2 saving. So, this one. So, this would be the appropriate SFK schedule for that economy, right? So, if we are choosing saving rate S2, then what would happen? S2 we know is greater than S gold. So K2 star is definitely greater than K gold, K star gold. And C2 star is less than C gold, right? Now imagine that starting from the steady state, the saving rate is reduced permanently to S gold. Let's say starting from S2, the savings rate is reduced to S gold. Okay. Now here you see that the per capita consumption, small c, given by the vertical distance between the FK schedule and the S gold times FK schedule. Initially, what it happens is, initially it increases by a very discrete amount. It's the initial increase of C, this much. So this is, we are moving from S2 to S gold. Initial reaction would be a quite substantial increase in per capita consumption, right? So per capita consumption, small c, it initially, this distance between these two schedules, this particular distance, it initially increases. And afterwards, what happens is the level of small c decreases monotonically during the transition. What's the new steady state value? And what is the new steady state value? The new steady state value is C gold. So economy, when we have shifted towards the S gold savings rate, economy would gradually move towards the golden steady state, right? So from here, we are slowly moving towards here. That is the K gold level of capital. This is where the economy would reach the steady state, and this would be the golden rule level of capital per unit of, right? So throughout this transition from K2 star to K gold, something that happens is the level of C falls monotonically during the transition towards the new steady state value C gold, right? So since C2 star. C2 star. Since C2 star is less than C gold, this this is the difference between the two schedules, and this difference at K gold, this difference represents C gold. This is something that we have looked into before. But C2 star is definitely less than C gold, right? It's obvious from the figure that C2 star is less than. So since C2 star is actually less than C gold, we can conclude that small c exceeds its previous value, C2 star, at all transitional dates, as well as in the new steady state. Hence, when small s is greater than S gold, the economy is over saving, in the sense that per capita consumption at all points in time could be raised by lowering the saving rate, right? So, an economy that sort of oversaves is said to be dynamically inefficient, because the path of per capita consumption lies below feasible alternative paths at all points in time, right? So if, on the other hand, s small s is, let's say, if it is less than s2, so if we are looking at s1, um, then what would happen is the steady state amount of per capita consumption can be increased. Just the reverse would happen. The steady state can be increased just by raising the saving rate, and this rise in saving rate would essentially reduce per capita consumption currently, and also during part of the transition period, and the outcome will therefore be viewed as good or bad depending on how households weigh today's consumption against the future consumption. How households weigh today's consumption against the path of future. So we cannot judge the desirability of an increase in saving rate in this particular situation until we make specific assumptions about how agents discount the future. For example, there might be some agents who would like to be, bit too prudent about the future. They would, there might be agents who you would consider to be risk averse, right? So, and also there might be agents who are more prone to taking risk, right? So you cannot judge the desirability of an increase in saving rate until you make specific assumptions about exactly how agents discount the future. So, so we are going to proceed along these lines with the next few lectures. Okay. So if you have a question regarding today's content, you can